Today we get to do something super, super fun. Probably one of the most fun things this whole semester. Of course, this is also pretty much the last thing we're doing this semester, but this is to talk about Taylor series. And the Taylor series, what these are is this is how we are going to represent known functions by using a series, okay? And so the Taylor series, which is named after a mathematician named Taylor, kind of obviously, this is a way to generate these series. So the question that we want to ask is, given f of x, can we write f of x as a power series centered at A? Or can we at least do it in, maybe we can't write it as a power series for all x, but maybe we can do it for some values of x near A. So at least in some radius of A. If we're lucky, then maybe we'll be able to do it for all real numbers, but we don't know that ahead of time. We're just going to have to see. So how would we do this? Well, I want you to think back for a minute to the problem of linear approximation or linearization. Recall that linear approximation the linearization of some function is given by f evaluated at A plus f prime of A times x minus A. And the idea is that the linearization evaluated at A should be equal to f of A, and also the first derivative evaluated at A should be equal to the first derivative of f evaluated at A. Now this gives us an idea, or it might give you an idea if you spent a bunch of time thinking about it. First of all, it gives me an idea that I need a better pen because this doesn't look very good. So let me grab a better pen, and then it will give us an idea of what to do. Where are the better pens? This is not a better pen. This, we hope, is a better pen. Okay, yes, better pen. Okay, this gives me an idea. If I want to approximate f of x near x equals A with Pn of x, a degree n polynomial, here's how I'm going to do it. Because it is a degree n polynomial, its first n derivatives are non-zero. So the function and its first n derivatives can be non-trivial. Once we hit derivative n plus 1, the whole thing is 0. So notice that Pn, the n plus 1 derivative of x, is equal to 0. That's because for a polynomial of degree n, after n derivatives, you get down to 0. Remember, every derivative decreases the degree by 1. A degree 0 is a constant. So once you do n derivatives, you are down to degree 0, and that's a constant. The n plus 1 derivative makes the constant go to 0. The derivative of a constant is always 0. So best we can do is for k equals 0 to n, we insist that the k derivative of the polynomial evaluated at A, excuse me, I wrote an X, but I want an A there. should be equal to the kth derivative of f evaluated at a. Now, first of all, notice that we consider the 0th derivative, that's just f of x or Pn of x. So, like, f0 of x is just f of x. That just makes it easier to write this as a single expression. Now, how could we get this to happen? Well, here's what I would like to observe. The kth derivative of x minus a to the nth power. Or rather, actually, I'm sorry, the kth derivative of x minus a to the k, this is actually going to be something that we can work out fairly easily. Because you take k derivatives. Each time you multiply by the exponent and you decrease the exponent by 1. Well, that means you multiply by k, then you multiply by k minus 1, then you multiply by k minus 2, all the way down until you multiply by 1. So this is actually just going to be k factorial. And it doesn't get anything else because at that point you are down to x minus a to the 0. You know, at that point this goes away because you're taking the derivative of something linear. So the derivative of x minus a to the k, if you take the kth derivative, excuse me, not the derivative, but the kth derivative is just k factorial. Okay, so what does that tell me though? Well, that means that if I write Pn of x is equal to the sum from, let's use k here, k equals 0 up to n of Bn times x minus a to the kth power, then notice that if I want to look at Pn evaluated at x, and I look at the kth derivative, all of the terms are going to be 0 at x equals... Why do I keep writing an x instead of an a? I want an a. There we go. If I evaluate this thing at a, then all of the terms are going to be 0 except for the constant term because they all involve an x minus a to the... Well, some of them will be taken away by taking k derivatives. But the rest of them will all be 0 except for the one that started at level k. Why? Again, I'm writing... very sloppy about that. I'm so sorry. That should be a bk as well. So this is actually going to be equal to k factorial times bk. So what that means is if I want this to be equal to the kth derivative of f evaluated at a, I need the kth term in this bk sequence. This is going to have to equal f evaluated at k, the kth derivative evaluated at a divided by k factorial. So this gives us our formula for the approximation. Pk of x is equal to the sum, pk, I keep switching my n's and my k's. Clearly, I should have done the n's and the k's backwards because that's what keeps happening in my head. I should have really written it that way, I guess. I didn't expect myself to have this kind of trouble keeping track of an n and a k. Okay, Pn of x is the sum from k equals 0 to n of the kth derivative evaluated at a divided by k factorial times x minus a raised to the k. There we go. This is the best polynomial approximation we can get at a of degree n. And this is called the Nth Taylor Polynomial at A for f. So obviously, to get a Taylor polynomial, we first need to specify a function, and then we also need to specify a point A. Now, the idea behind what we're really interested in, because on the one hand, you may want to get a polynomial approximation, because maybe all you need to do is to get something approximate near some point. And for that purpose, a finite polynomial approximation might be fine. But in general, no polynomial can be equal to, say, e to the x, right? Because e to the x, all of its derivatives are non-zero. A polynomial always has derivatives that are equal to 0 after a certain point. So you cannot have any polynomial be equal to e to the x. You cannot have a polynomial equal to sine x or cosine x because no polynomial can be periodic. One way of seeing that is like sine x and cosine x, they have an infinite number of zeros. Well, no polynomial can have an infinite number of roots. Okay, so you can never get an exact expression for these in terms of polynomials. But what we're hoping for is that we can express them in terms of a power series. So this leads us to the idea of the Taylor series, which is basically, what if we let the degree of the polynomial go to infinity? The Taylor series for f at A, this is going to be the sum from k equals 0 to infinity of the kth derivative evaluated at A divided by k factorial times x minus a raised to the k. There we go. So really, this Taylor series, you can kind of think of it as an infinite degree polynomial, just like we can think of power series in general as an infinite degree polynomial. Now that's not precise. It's not a rigorous definition, but it kind of helps your intuition a little bit sometimes to think of it that way. We're really just asking, can we get better and better approximations with polynomials as we let the degree of the polynomial approximation go to infinity? Now, this in and of itself is not all that groundbreaking. I mean, it's really interesting. It's a really interesting result, but in some sense, it's not all that tricky. In some sense, like, it seems tricky, but to somebody who's done a lot of mathematics, the whole argument was just, well, let's write down a polynomial whose derivatives are what we want them to be. Okay, this is what we need the coefficients to be to get those derivatives. Okay, we're done. The problem, and this is the really big question, is this. Does this series converge to f of x? Or rather, for which x does it converge to f of x? Because here's the problem, okay? Even the infinite series does not have to converge to the original function that we had. Even though it's got all the right derivatives at A, that doesn't mean that it necessarily is equal to the original function. Now, we can hope for a suitably nice function that will be true. And as we're about to see, it is true for a lot of functions that we're interested in. But it's not something that can be true in general, okay? So you do have to be really careful here. And this is where Taylor's famous result really comes in. Because this formula, again, it's a great formula. It's super useful. It turns out to have lots of nice properties. But just coming up with this formula by itself doesn't really show us how useful this formula is. I think the real reason why we named this after Taylor is because he's the one who came up with a way of showing when this is guaranteed to be useful. Now, before we show you that, let me tell you one other quick thing. If A equals 0, this is also called a Maclaurin series. So I don't know the history of this, why in the special case of A equals 0, this is called a Maclaurin series. Apparently Maclaurin did something with these series with A equals 0. Now, a lot of the examples that we are going to look at are actually going to be Maclaurin series and thus a special case of Taylor series. But I want to talk to you in general terms that will apply to all Taylor series. This is Taylor's famous result. And this is why the Taylor series is so useful for so many functions. So Taylor proved the following result. He proved that for any f of x with Taylor polynomials Pn of x, f of x is equal to Pn of x plus Rn of x for some Rn of x. Now, that in itself is obvious, okay? Because take Rn of x to be f of x minus the Taylor polynomial. That is obviously a function. Yes, if all he said was this would be like almost worthless, okay? I mean, it's not totally worthless, but like it's not anything of any interest at all in itself. Here is what he was able to prove. He was able to prove that where what he showed is that Rn of x is equal to the n plus 1th derivative evaluated at c over n plus 1 factorial times x minus a. Okay, I don't have room here. Let me rewrite this on the next line because this is a tiny whiteboard. So Rn of x is going to be equal to the n plus 1th derivative of f evaluated at c over n plus 1 factorial times x minus a to the n plus 1 for some c. Where is c again? It is in between a and x. So, this is Taylor's remainder theorem. Now, I am not going to prove the remainder theorem for you today because, frankly, the proof is pretty technical and I mean, like a part of me is very tempted to prove it, but I think it's not really worth proving. The proof kind of is like think of like a really massive version of the mean value theorem. So go back to the mean value theorem. Look at how we proved that. It's a very similar kind of idea because remember what the mean value theorem tells you is there is a point between these two where it has to be equal to the, where the average rate of change is equal to the derivative. Well, this is sort of the same thing, just jacked up to higher derivatives, okay? So we're just bumping up the levels here to the higher derivatives. The complexity of the proof also goes up in the process, but it's one of those things that's like not so complicated. I think you can understand it. I just don't want to take the time, okay? That's really what I'm saying. So if you're interested, you can look up a proof, and I think you would be able to understand it just fine. I just don't want to take 20 minutes to explain the whole thing to you right now. I'd rather look at some examples of how useful this kind of thing is, okay? So, 2 points of use on this. Use number 1, you can estimate the error. So let's say that you want to estimate the error. Well, here is where we can come up with a really nice bound on the error. The bound on the error for the nth Taylor polynomial on the interval from a minus x up to a plus x, here is what we need to do. Let mn plus 1 be a bound such that the absolute value of fn plus 1 of x is less than or equal to mn plus 1 on the interval a minus x to a plus x. Then on this interval, in fact, if you want to do an even smaller interval, you can. Like you could just do a up to x or whatever. Well, then what we can say is that Rn of x is going to have to be less than or equal to, if we replace that n plus 1th derivative, we can say it has to be less than or equal to mn plus 1, or the absolute value has to be less than or equal to mn plus 1 over n plus 1 factorial times x minus a to the n plus 1. And this is what is known as the error. Yeah, so really, I guess what I should say is let's go from a up to a plus x. Or from a plus x up to a, because maybe x is like maybe we're at a negative, like to the left of a. So this is the error estimation theorem. Now, thing one that we can do with this, if I give you a Taylor polynomial and I say, okay, I need to make sure that on some specified interval, and in fact, I should say this works really on any interval. So never mind a to a plus x. Like this is just any interval around a. You find this bound so that it holds on the entire interval around a, and that's all you really need. So I didn't write that very precisely, but I'll let you work out the details yourselves. I trust those of you at this point who have made it to this kind of a class to be able to say, oh yeah, we can rewrite this with another interval and it all makes sense. So the first thing we can do is we can do something like, if I tell you, okay, I want to get an approximation for e to the x that works between -1 and +1. So I'm going to do Taylor polynomials at 0. How do I guarantee that my error is going to be below some fixed tolerance? Well, the answer is you figure out what is the bound on the nth derivative of e to the x on this interval, and then you just find what do I need to take n to be equal to make sure that this error bound is below the tolerance. It's actually pretty straightforward. So that is one of the practical uses of this thing. If I want to approximate a function with a polynomial, this allows me to do it. However, that is not actually the most interesting mathematical, or sort of like for calculus purposes, that's not the really interesting part. The really interesting result is this. Suppose for some x, Rn of x goes to 0 as n goes to infinity. Then the error in the Taylor polynomials is going to 0 which means the limit of the Taylor polynomials, which is going to be the sum from k equals 0 to infinity of kth derivative evaluated at a divided by k factorial times x minus a to the k, is equal to f of x for that value of x. In other words, our series does equal our function wherever Taylor's remainder goes to 0. And this is where things are going to get really, really cool, because this is the thing that is going to let us express our functions as power series, and it's going to guarantee that our power series converges to the right thing, to the, like, not just is it going to converge, it's also going to converge to the correct thing. It's usually relatively easy to show that these power series are going to converge, but then it's actually often not that much more difficult to show that the remainder is going to converge as well. So I want to demonstrate for you how you do this with some examples. Let us find the Maclaurin series for f of x equals e to the x and show it converges, and it converges to e to the x. Actually, I take back what I said. So one really quick thing. Yeah, one really quick thing I want to be careful about here, because to be honest, this is a technical point and I need to think about it a little bit more. If Taylor's remainder theorem goes to 0, does that guarantee that the series itself converges? I think the answer is probably yes, but I don't want to say that for sure. So it might be that for Taylor's remainder theorem to work, you have to actually assume that the series converges. Well, no, that can't be true, because, yeah, I'm pretty sure that if the remainder goes to 0, that also shows it converges. But we're going to show this converges and then show it converges to the right thing anyway, just because it's actually not much more work at all. So first of all, we want to find what is the kth derivative of 0. Well, here's the thing. The kth derivative, in this case, evaluated at x, is literally just e to the x, because all derivatives of e to the x are e to the x. Therefore, this is going to be e to the 0, which is going to be equal to 1. That means that in the power series, all of these coefficients are going to be 1. So our series is going to be the sum from k equals 0 to infinity of 1 over k factorial times x to the k, which we usually just write because why not? We will write it as x to the k over k factorial. This is one of the most famous series in mathematics, probably the most famous power series that there is, because it's the power series expansion of e to the x. In fact, some mathematicians, when they're sort of like rigorously doing calculus from the start, to make things easy on themselves, they define e to the x using this series. There are reasons why you might want to do that, but it's a trade-off. See, the thing is, proving e to the x is differentiable with the usual definition of e to the x as an exponential function is a royal pain. Proving that this is differentiable and has all the nice properties is quite simple. The trade-off is that then, in order to even define this, you have to be able to define series and their convergence. So there's upsides and there's downsides to the different ways of getting through all of calculus. Okay, so now, does this converge? Well, let's look at the ratio test. So we will be looking at the limit as k goes to infinity of the absolute value of x to the k plus 1 over k plus 1 factorial times k factorial over x to the k. This is equal to the limit as k goes to, that's a 0, infinity of absolute value of x divided by k plus 1. That is equal to 0. Yep, this thing is absolutely convergent for all x. So the first interesting thing that we have seen is that this power series does define a well-defined function for all real numbers. Its radius of convergence is infinite. The next thing that I would like to observe is, or the next thing I want to calculate is, does this converge to e to the x? Well, in order to figure that out, let's write down the remainder. Or rather, a bound on the remainder. So the absolute value Rn of x, is this bounded? The answer is yes, because consider this. The k plus 1 derivative is still just e to the x. And on the interval from minus x up to x, minus absolute value x up to absolute value x, that's a better way of writing it, e to the x is bound, or let me write it this way. Let's use a t here since I'm using x for something else. E to the t is bounded by e to the absolute value of x. So yes, it is in fact bounded. That means that absolute value Rn evaluated in x is going to be less than or equal to e to the x, and then we have absolute value of x minus a raised to the n plus 1, all divided by n plus 1 factorial. Now, does this go to 0? Yes, it does. Why do I know this goes to 0? Because the sum of e to the x times absolute value, whoops, that's not what I wanted to write, x minus a raised to the n plus 1 divided by n plus 1 factorial is absolutely convergent. We actually just showed that a minute ago, because this is basically the same series as this. Oh, and in fact, our a here is 0. Why am I even bothering with an a? Well, the fact is you could do a Taylor series for e to the x around other points as well, and you would get a similar kind of thing. You could show the Taylor series converges. So we showed that this is absolutely convergent. But if this is absolutely convergent, then this sequence has to go to 0 by the divergence theorem. So this means the limit as n goes to infinity, e to the x, absolute value of x to the n plus 1 over n plus 1 factorial is going to 0. Because remember, if this doesn't go to 0, the series can't converge. So what we just proved is not only does this define a function, it actually defines a function that converges to e to the x for all values of x. So for any x, e to the x is the sum from k equals 0 to infinity of x to the k over k factorial. That is what we just proved. Now, a little bit of terminology here. If f of x is equal to its Taylor series, at A on some interval, we call it real analytic on that interval. If it is equal to its Taylor series or any power series for all real numbers, then we just call it real analytic. Here's the other interesting thing to notice about this formula, though. So I wanted to give you that bit of terminology, but returning to this fact, this is true for any real number. But this formula converges actually for any complex number as well. And so we can use this to define e to the x for complex x. Because the thing is, this is always convergent, and it agrees with e to the x for all real numbers. So we may as well use this to define it for complex numbers as well. Like, that makes sense. This is one of the really powerful things about series when we are talking about real analytic functions. If the series converges with some radius of convergence, then we can extend it off the real number line and define, the series works for complex numbers. That means we can extend our function to complex numbers, at least within the radius of convergence. Now, in this case, the radius of convergence is infinite, so we can do it for all the complex numbers. All right. Now that we've got all this stuff worked out, I want to show you something else. Let's do the same kind of thing for sine x and cosine x. Actually, I'm going to do sine x, and then I'm going to leave cosine x as a little exercise for you. So, Maclaurin series for sine x. So I'm going to have f of x equals sine x. Now, here's the interesting thing. Notice that the derivatives follow this pattern. The 4k derivatives, these are always going to be equal to sine x. And if I evaluate this at x equals 0, this is always going to be 0. The 4k plus 1 derivatives, these are going to be cosine x. Evaluate that at 0, and we get 1. The 4k plus 1 derivatives, these are going to give me negative sine x. That gives me a 0 at 0 again. I'm sorry, that's a plus 2, not a plus 1. And the 4k plus 3 derivatives, these are going to give me negative cosine x. When I evaluate that at 0, that gives me a minus 1. So, for odd numbers, we get a plus or a minus 1, and it keeps flipping back and forth. So our series is going to be the sum from how do I want to write this? Let me back up a second, and there's several ways of writing this, and I want to write it in the way that's usually considered most standard. So, yeah, this is the way we usually write it out. I've lost my pen. Okay, I found my pen. We write this as the sum from k equals 0 to infinity of minus 1 to the k divided by 2k plus 1 factorial. This is only going to pick up the odds times x to the 2k plus 1. Now, to show that this converges, you use the ratio theorem. To show that the series converges to sine of x, you use the same method as we did before, okay? You show that the Taylor remainder converges, and in fact, it's even easier than before, because in this case, the bound on each of your, the bound on the derivatives of sine x, any derivative of sine x is bounded between -1 and +1. So your mn is always just equal to 1. Like, you can always just take it to be equal to 1, and that's fine. So this is actually very easy to show it converges. Now, I want to do cosine as well, but this one I'm going to leave to you to figure out. It's really similar to the sine example, except everything gets shifted by 1. So, like, you bring the cosine back up here, and the sine goes down to the bottom. So let us now write down the Maclaurin series for cosine x. This is going to be the sum from k equals 0 to infinity of, why have I lost it? It was around here somewhere, and I want to make sure that I write down the right thing. Yeah, this is going to be -1 to the k over 2k factorial times x to the 2k. Beautiful. And once again, the fact that this converges, ratio theorem. The fact that the remainder goes to 0 follows from the fact, well, it's very similar to what we did for e to the x, okay? And, except that we get an even nicer bound. So it's almost identical. So in fact, this converges to cosine of x for any value of x. Now, from this and from the Maclaurin series for sine x, we can now define sine and cosine for all imaginary or for all complex numbers as well. But here's what I want to do to show you something really interesting. We are going to prove something called Euler's identity. It's not really his. Somebody else definitely came up with this. I cannot think of his name. It was like Kahn or something like this. Somebody else came up with this identity, but it gets associated with Euler an awful lot. I don't know why. It's possible, actually, that somebody else came up with it in a different way. Like, Euler may have been the first person to really do this right or something. I don't know. The fact is that the history of mathematics is often filled with really confusing, somebody did something, but then somebody else found that they did it wrong and fixed it, and the name of it sometimes gets associated with the first person, sometimes with the person who fixed it. Sometimes the first person just did it right, and then somebody else came along and did it, and it got associated with the second person. It's all a confusing mess. So don't take the names of things too seriously in mathematics all the time. So here is what I want to look at. Let's write down e to the ix. Well, this is going to be equal to the sum from k equals 0 to infinity of ix to the k divided by k factorial. This is going to be the sum from k equals 0 to infinity of let me think of how, let me explain this in the following. Well, actually, let's write it down this way. It's going to be I to the k, x to the k over k factorial. Now, what is I to the k? So notice that I to the k has a few possibilities. If k is equal to 4 times n, actually, let me write this out this way. If k is a multiple of 4, then this is equal to 1. If k is equal to 4n plus 1, this is equal to I. If k is equal to 4n plus 2, this is equal to minus 1. And if k is equal to 4n plus 3, this is equal to minus I. And it keeps on repeating like this. So Let us now think about what this actually comes out to be. Well, this is therefore going to be able to be split into two sums. It's going to be the sum from k equals 0 to infinity of minus 1 to the k plus another sum from k equals 0 to infinity, except this one is going to be multiplied by an I, and it's also going to have a minus 1 to the k. Now, when you work out what these are going to be, this one here is going to be all of the even powers. So this is going to be x to the 2k over 2k factorial. This is going to be the odd powers. X to the 2k plus 1 divided by 2k plus 1 factorial. Now, I'm allowed to split up the series this way because we know it is a convergent series. So I can split it into these sub-pieces as long as they converge as well. Well, check it. These both converge using the ratio test, so we're fine. But actually, you may recognize these as something we wrote down like 5 minutes ago. Does anybody recognize what these two series are? This one and this one. So this is actually the cosine of x, and this is I times the sine of x. So what we have shown is that e to the I x is actually cosine x plus I sine x. This is one of the most famous formulas in mathematics, okay? Or equations in mathematics, identities in mathematics. And you prove it in a pretty straightforward way by using these series. Now, one of the most famous applications of this is going to be that e to the I pi is the cosine of pi plus I sine pi, which is equal to minus 1. Sometimes this is called Euler's identity itself. Another thing that you can do with this is you can prove that the cosine of x is actually equal to e to the I x plus e to the minus I x divided by 2. And you can get a similar formula for sine of x. So you get, oh crap. What is the formula for sine x? Now I gotta look it up to make sure I don't get everything screwy. It is, yes, e to the I x minus e to the minus I x divided by 2, except we have to multiply the whole thing by minus I. So we get all these nice relationships between the trig functions and the exponentials. And what you'll notice is really interesting here. Well, I mean, there's a lot of things that are of interest here, but you can basically build the exponential out of the trig functions, and you can actually define the trig functions in terms of the exponential functions, if you allow yourself to use complex numbers. Now, the problem, the reason why people don't start things this way is because to define all of these for the complex numbers, you need to be able to use these series. Okay, so I hope that I have shown you some stuff that is of interest to you today. I have a couple more things that I really quickly want to mention. These are not directly connected to Taylor series, and we're not really going to use it, but I do want to mention it really quickly. There is another way of representing periodic functions using what are called Fourier series. The idea behind a Fourier series is we can write down the Fourier series. One quick thing that I want to mention actually before I do that. If you go back and you look at the sine and the cosine, you'll notice the Taylor series for cosine only involved even powers of x, and the Taylor series for sine only involved odd powers of x. That is not surprising because we have reflective symmetries. So cosine is even, but odd powers of x do not have even symmetry. So there's really no big surprise that that no odd powers show up. Similarly, sine is an odd function. It has odd symmetry. Even powers of x do not have odd symmetry, so it is not surprising that only odd powers showed up. Okay, so a Fourier series looks like this. The sum from k equals 0, or actually we can do n equals 0 to infinity of b sub n e to the I times n times x. Although sometimes we also have another factor up here as well. So we might have some factor like k or something thrown in there. It just kind of depends upon what we are trying to do here. Often people include a factor of 2 pi to make things nice and simple. Now, the reason these Fourier series are nice, and by the way, sometimes people use cosine and sine instead. So like you can take the real part of this or the imaginary part of it. The real part will give you a cosine from what we just said. The imaginary part gives you a sine. The reason why this is of so much interest is because any periodic function, subject possibly to some minor conditions on it being nicely behaved, is going to have a Fourier series expansion. And these Fourier series can then be truncated and approximated by cutting off the series after a certain point. Well, sound waves can be thought of as a bunch of periodic functions. That means sound waves can be encoded by encoding the coefficients in their Fourier series, possibly terminating after a certain point. And this is how people digitally encode audio, or it's one way to digitally encode audio. And here's the thing that you have to do in order to make this work so that it sounds right. You just have to wait to truncate your series until n is large enough that the human ear can no longer detect those frequencies. So the larger the n, the higher the frequency of this periodic function that's spinning around, or that's repeating itself. Well, eventually you get so high that people no longer hear those frequencies, and as long as you only cut off the Taylor series past that point, people can't really tell a difference. Now, I'm not sure if that is 100% true or if that's only mostly true. I am not an expert on digitally encoding music and things, so some people will still say, well, records sound better still. And it's possible they do, because it is possible that the human ear can detect certain times when the shape of the waveform gets really different because of those high frequencies. I don't know. Maybe that can occasionally happen. But in general, you won't be able to tell the difference as long as you wait. There is also a really interesting thing that you can do with this, which is that you can sketch any repeating pattern that you want to by using a Fourier series like this. And so you may wonder, like back in the day, when they didn't realize that it makes most sense in physics to consider the sun as the central point of the solar system. Actually, you want to consider the center of mass of the solar system as the center, but they didn't think about that. They would think of the Earth as the center, and they would try to draw everything else moving around the Earth. But the funny thing was, they actually came up with some really accurate astronomical models this way. How were they able to do that? Well, the answer is that what they were really doing is they were writing something that was called the epicycle, or they called them epicycles. Basically, one thing circles another, but then it also circles the point it's circling, and it circles that point that it's circling, and it keeps on doing this. Essentially, what they were doing was writing down truncated Fourier series. But a truncated Fourier series can approximate anything. So I will link for you a video in which someone shows how you can draw Homer Simpson by using this method. Okay, so this has been a rather lengthy video here, and the good thing is, like, for the past 10 or 15 minutes, we've just been talking about neat stuff, not stuff you're going to be tested on. But this is our final video for Calculus 2, at least for now. So, yeah, let me know if you have any questions. Make sure to check on Blackboard for, homework and test information and the final exam information. And I hope that you've enjoyed this class. It's nice for me to be able to talk about some, more advanced mathematical concepts here. So I always enjoy when I get to do that kind of thing. And let me know if you have any questions. And good luck.